A gente pode
Ah,
tentar aqui fazer como se fazer a apresentação, se você, só para testar, para ver se funciona.
tá bem. Tudo bom.
Muy bien.
Buenas
a todos
tardes.
en América Latina.
Vamos a dar el primer paso al profesor Duván Cardona de la Universidad de Gante, quien dará la apertura del seminario, y paso siguiente estaremos con nuestro expositor del día de hoy. Por favor, Duván.
Muchas gracias, profesor Richard. Buenas tardes a todos en América Latina. Estoy complacido de darle la bienvenida a Matemáticas y Memoria, un seminario de análisis y ecuaciones diferenciales para Latinoamérica. Quiero agradecer a Santiago Correa de la Universidad Nacional de Colombia, sede Medellín, a Tobías Castro de la Universidad del Atlántico, a Alex Pico Amaya de la Corporación Universitaria Latinoamericana y a Richard de la Cruz de la UPTC, Universidad Pedagógica y Tecnológica de Colombia, por el esfuerzo conjunto en la organización de este seminario. Compartiré algunas palabras sobre nuestro seminario y su contexto. Desde la invención del cálculo por Newton y Leibniz en el siglo XVII, seguido por los fundamentos establecidos por Cauchy en el siglo XIX, el análisis matemático ha sido una rama fundamental que ha entrelazado diversas áreas de las matemáticas. Hoy en día lo conocemos como análisis simplemente y lo asociamos con el rigor, el mismo que las mentes más brillantes han nutrido a través del hermoso ejercicio de la investigación matemática. Figuras como Poisson, Liouville y Fourier utilizaron estos fundamentos e introdujeron las ecuaciones en derivadas parciales, junto con el método de la transformada de Fourier, como herramienta para resolver modelos específicos, como la ecuación del calor o la ecuación de onda, mediante el método de separación de variables, lo que condujo a la invención del análisis armónico. En la actualidad, gracias a las contribuciones del siglo pasado, como la teoría de los espacios de Banach y toda la maquinaria del análisis funcional, utilizamos el análisis y las ecuaciones diferenciales como herramientas selectas para comprender el mundo. Lo hacemos a través de modelos descritos por ecuaciones en derivadas parciales y de las aproximaciones a estos modelos que entendemos mediante el análisis numérico y la computación. Pensar que la investigación matemática, especialmente en el área del análisis, pertenece únicamente a mentes europeas o a científicos de las regiones más desarrolladas del mundo es una idea del pasado. Alberto Calderón, un matemático argentino, junto con Anthony Sigmund, establecieron la Escuela de Análisis de Chicago y formaron una nueva rama del análisis conocida como las integrales singulares. Su artículo de 1952 en Acta Matemática ha sido quizás uno de los más influyentes en el área del análisis en los últimos 72 años. Imaginar que un matemático argentino fue capaz de crear una subrama del análisis y estar en el primer nivel en la comunidad matemática a nivel internacional es algo que no podemos olvidar. De esa escuela han surgido figuras como el Einstein y los medallistas Fields, Charlie Pfefferman y Terry Tao. Desde esta región, desde este borde del mundo, han surgido analistas que nos representan a nivel mundial. Carlos Koenig, un matemático argentino, ha sido presidente de la Unión Matemática Internacional, entre otros muchos logros. Luis Caffarelli ha ganado el premio Abel y la colombiana Tatiana Toro es actualmente vicepresidente de la Unión Matemática Internacional. Todos estos nombres de una u otra forma están relacionados con el análisis y las ecuaciones diferenciales y son latinos. Este seminario es un llamado para no olvidar la memoria de los grandes matemáticos que hemos tenido en América Latina. Es un llamado para promover con fuerza nuestra investigación matemática y para publicar nuestros resultados, comprometiéndonos a realizar investigaciones de calidad con resultados publicables y aplicables. América Latina ya cuenta con un medallista Fields. Tal vez el próximo esté entre nosotros. Tal vez lo veamos pronto. Así como la literatura vivió una época dorada con el boom latinoamericano de escritores como Carlos Fuentes, García Márquez, Octavio Paz y Mario Vargas Llosa, algunos de los cuales incluso fueron galardonados con el prestigioso Premio Nobel, los matemáticos estamos al borde de una era dorada de las matemáticas en América Latina. Para recordar a nuestros matemáticos latinoamericanos más célebres y para compartir los avances recientes en el análisis y las ecuaciones diferenciales, nos reunimos hoy y en unos minutos daremos paso a la charla del profesor Vladimir Neves. Su conferencia, así como algunas sesiones futuras de este seminario, estarán dedicadas a José Fernando Escobar, uno de los titanes de las matemáticas que siguen la memoria de muchas generaciones en Colombia. Recordemos, José Fernando Escobar nació en Manizales el 20 de diciembre de 1954, estudió matemáticas en la Universidad del Valle, en Colombia, y gracias a una beca ofrecida por el Instituto de Matemática Pura y Aplicada INPA, obtuvo su grado de maestría en Río de Janeiro, Brasil, donde compartió escenario con importantes matemáticos latinoamericanos que influyeron su carrera. Posteriormente, completó su doctorado en la Universidad de California, Berkeley, en el 86. Fue profesor en destacadas universidades y centros académicos en Estados Unidos. En el 94 se unió al Departamento de Matemáticas de la Universidad de Cornell, donde graduó muchos estudiantes, especialmente latinoamericanos. En palabras de Bob Stricker, José Fernando Escobar siempre fue capaz de entender la profundidad de los problemas y enfrentarlos directamente. Falleció en un periodo sabático en la Universidad del Valle el 3 de enero del 2004. Después de este recorrido, los dejo con el profesor Richard de la Cruz. Muchas gracias a todos por estar conectados.
Richard, activa tu micrófono, por favor.
Muchas gracias, Duván, y agradezco también a los participantes de este seminario, así como también al profesor Vladimir Neves por haber aceptado esta invitación a este seminario, que para nosotros, los organizadores, es muy importante, ya que queremos unir, digamos, ese sentimiento matemático que tenemos a nivel de nuestras regiones. Para mí es un gran honor presentar entonces al profesor Vladimir. Él es el director del Instituto de Matemática de la Universidad Federal de Río de Janeiro. Él realizó sus estudios de doctorado en Brasil, en compañía entre el INPA y la Universidad Federal de Río de Janeiro. Tiene un postdoctorado en la Escuela Normal de Lyon, en Francia. Ha sido profesor visitante en la Universidad de Oxford. Ha dirigido una gran cantidad de tesis de maestría y doctorado, lo cual pues es un gran, digamos, una gran colaboración hacia la comunidad matemática, tanto a nivel de Brasil, y ha tenido estudiantes de otras regiones fuera de Brasil, de Perú, en general de Latinoamérica, lo cual pues nos liga directamente con este seminario. Dentro de sus actividades en investigación, él trabaja en ecuaciones diferenciales parciales, en ecuaciones de evolución, leyes de conservación, mecánica del continuo, fenómenos no lineales, para modelación de dinámicas complejas no lineales. Y en este día nos comparte la charla titulada The Hard-Short Free Boundary Limit of the Buckley-Leverett System. Professor Vladimir Neves, please. Thanks for accept my invitation to the seminar.
Ok. Eu vou falar em português, o agradecimento. Todos me ouvem? Sim, Richard?
Sim.
Sim, ok.
Tudo bom.
Eu vou iniciar em português. Como é um evento sul-americano, né? Eu deveria estar falando espanhol. Eu posso compreender bem espanhol, mas não falo tão bem assim. Eu, primeiramente, desejo um enorme sucesso a este evento de vocês. Parabenizo pela ideia de ter construído isso, né? O nome do homenageado, né, José Escobar, sem sombra de dúvida, um excelente nome, né? Escolheram muito bem, né? Espero poder estar contribuindo à altura aqui nesse primeiro dia, nessa primeira palestra, né? E agradeço não só ao Richard, mas como os outros, o Santiago, o Castro e os demais, todos que organizaram essa palestra e que concordaram que eu pudesse estar aqui falando um pouquinho de um problema que eu trabalhei durante alguns anos, né? E vou dar aqui uma visão do que a gente fez nesses últimos 2 anos. Então, mais uma vez, muito obrigado e uma honra estar participando aqui com vocês e espero poder estar à altura aí do que vocês estão pretendendo. So now I'm going to change to English, and then, as Richard said before, I'm going to talk about the Harris-Shaw free boundary limit of Berkeley systems. So in fact, I'm going to talk about which is Berkeley system mean, okay? This is a joint work with André de Oliveira Gomes, a Portuguese colleague. In fact, he started with a postdoc here. And then let us try to start so the outline of my talk. So I'm going to show you what this problem is, and will be the introduction. So I try to convince you that this problem is interesting. Then we pass to some difficulties to show the existence of solution of this problem, and some previous works that have been done, in particular, change the system. Then I present you the new approach, what we are going to propose, or have already been proposed, and the strategy to solve this system. And then I go to show you the many steps to show the existence of weak solutions. Okay, I'm not going to make some counts, I'm just telling you what are the steps, and then at the end you could ask me anything, and I'll try to tell you what it could be. So the Berkeley system has been studied by many authors, in fact, because it plays an important role in the wide range of planar and operation oil wheels, filtration problems, dam studs, and also in a large class of interesting similar mathematical models. So I give you two books, Chavin-Chavret book and Bustos-Concher-Burger book, which tell much about this type of problems, like, for the filtration in particular, the second book, and also for the porous media equation, okay? So the most prototypical example is the encroachment of water into an oil sand. So you have oil and water crossing some flow mixture with two fluids flowing in a porous media. I should say that this is the most example from the oil industry. But let's tell you what is the Berkeley system. So it consists of conservation law, a scalar conservation law, that expresses the mass balance for the density, which I call U of Tx, so depend on T, the time T in the space X, of the fluid mixture involving, so the density of the fluid mixture, involving a nonlinear continuity equation. So you have the partial derivative of U, the density with respect to time, in divergence with respect to X, of G of U V. Of G of U V is called the flux function. So this is a usual scalar conservation law. And then, where G of U represents an additional volume filling term in the density flux, and V, this V of Tx, is the velocity, used to be called the C-page velocity field, which is given by this equation, H of U V, some nonlinear function H that depends on the density U, times the velocity V, equals a minus gradient of P. This formula is obtained from the empirical Darcy law when you apply it for each component of the mixture, which describes the dynamics of the flow, the velocity, in relation with the scalar function P of the X, which we usually call pressure. Indeed, you observe here that P is not the pressure given by some law of state, not given by some constitutive relation, but is related to the incompressibility condition for the velocity vector field. P looks like a Lagrange multiplier of the constraint divergence of B equals 0. So you have the incompressibility condition that tells you the divergence of the velocity should be 0. So you have three equations, and then we could write, for instance, if you write V equals a minus gradient of P divided by H of U, and you plug this V in this constitutive equation, Then we may write the so-called book-level system as this equation, which looks like a power limit equation, but in fact is a filtration equation, dt of u minus divergence in x of capital theta of u gradient p equals 0. And the second equation is divergence of the velocity, or in particular, the gradient of p divided by h of u equals 0. As written here, where capital theta of u is g of u divided by h of u is bigger or equal h naught or h0 for some h0 strictly positive. Just to tell you some physical meaning, the inverse of h has the meaning of total mobility. And recall that this system 1 is also called the weak formulation of multidimensional Muscat problem. So I'm not concerned here just in dimension 2, dimension could be 3 as well. So this formulation, this formulation of the book-level systems is also called the weak formulation of the multidimensional Muscat problem. So we could put this system, we could pose it in 0 capital T times omega for any T positive and omega containing RD, an open bounded domain. I'm going direct to the bounded domain. So, since we are in a bounded domain, you have to prescribe some influx or an outflux of the flow at the boundary of omega, where we are going to denote by gamma, capital gamma. That is, this flux that comes from the equation, so the gradient of u, that of u gradient of p, times scalar product with n should be equal f on the boundary gamma t, where n of r denotes the unitary normal unitary vector field at point r of gamma. Gamma t is 0t times capital gamma, and f is some given data which I call a normal boundary flux, and you have to consider that the modulus of this function should be bigger than some fb for some fb strictly positive. For that system, also with this boundary condition, normal boundary condition, have to consider also for the equation 1 should be supplemented with initial data for the density. So you have at time t equals 0, u of 0x should be equal 0 of x in omega. Okay, so you have this system combined with this boundary condition in Neumann sense in the initial condition for the density, and to use it as a non-negative function, given a non-negative function. Okay, so I give you the model, and I'd like to tell you why it's difficult to resolve this problem. So I'm talking about difficulties and previous works. First, you observe from the book-level system that the velocity v is expected to be just a L2 vector field. It's just integration by parts, okay? So this velocity just in L2 means that you have to treat a scalar conservation law in the class of Rogli coefficients. So the flux function has low regularity. So the mathematical problem of proving global well-posedness of weak solution for the book-level system is a mathematical challenge. I mean, the well-posedness. In fact, the main question of showing existence of weak solution remains open for many decades. So no one knows how to resolve this, and I propose a new idea to resolve it. Okay? So, moreover, due to the presence of discontinuity, I mean, you are working with a scalar conservation law, you have shocks, so the entropy formulation is usually adopted. So since you could start with initial data with smooth enough, but you could develop jumps in a finite time. In particular, if one tries to use the cinetic formulation of scalar conservation laws to resolve the system, then it's well known that we do not have the Pernalion renormalization property for the associated transport equation when the drift vector field is just in L2. I mean, when we start with the scalar conservation law, we use the entropy formulation, you differentiate with respect to the cinetic parameter, you get a transport equation, and this transport equation does not have enough regularity of the drift vector field to have this renormalization techniques from the Pernillon's or also Ambrosio renormalization procedure, used to call Ambrosio renormalization procedure, with just this regularity of L2 of the vector of the drift vector field. And this renormalization procedure in particular is very important to show compactness of approaching sequence of regular solutions using, for instance, the idea of the rigid result of perturbed Dalibard. I mean, if you try to resolve this approaching by some perturbation with the Laplace of U, epsilon Laplace of U, and you try to get compactness using this idea of the perturbed Dalibard, it's not so possible. It's not possible because you do not have enough regularity of drift vector fields. But there are other ways to resolve the scalar conservation laws. And then we will also observe that the function g of uv, so the flux function, is degenerated. That is, there exists a Kc in a sphere that the mapping for each lambda, g of lambda v of tx dot Kc, is constant on non-degenerative intervals with respect to lambda for tx and an open set containing 0t times omega, Cartesian omega. Therefore, since this flux function g of uv is degenerated, there is no hope to apply H measures theory associated with the measure of our solution for conservation laws. Particularly the papers from Eugenie Panov and so on. Or similar, we could not apply the cinetic theory introduced by the Lyons, Perton, and Tademont, because of this flux functions is degenerated. So it's not possible to apply the cinetic theory to get compactness using this non-degenerated condition. It does not work either. Okay, so some previous work that people have tried to resolve this problem. To overcome the difficulties mentioned above, the bulk level resistance has been significantly modified in some directions. A quite general case, in general, can be described by the following partial differential equations. So given non-negative viscosity functions, mu and nu, we have. So now you consider your scalar conservation law plug with a smooth term, or a diffusive term with divergence of mu gradient of u plus some external force term capital F. And your equation for the velocity, you plug a minus divergence of nu, the symmetric part of the gradient of v, plus h of v equal a minus gradient of v. So it looks like a Stokes equation for the velocity. Okay? As said here, F and G, capital F and capital G are external forcing terms. Not so important, but the capital D is the symmetric part of the gradient operator, and the above system certainly should be supplemented with suitable initial conditions, initial and boundary conditions. So what you have done to get the idea, before you have partial with respect to u plus divergence of g of uv equals 0. Now you plug this diffusive term, and then before you have h of uv equal minus gradient of p, and now you have this diffusive term in both equations. Okay, so somehow this is the most general idea, or one of the most general idea. Okay, but there are two directions, principal directions. There exists a list of important papers related to this system 3. Okay, in particular, following the two main directions. You could consider mu positive and nu equals 0, or nu equals 0 and mu positive. And I'm going to tell you two papers in each of these cases. So the first one is from Kruskov in Sukorzansky. And this paper I'm not going to read here, but it's the boundary value problem for system of equation 2-phase filtration type. They are able to show that the system 3 is L-posit in the class of semi-classical solutions. So this definition of semi-classical solutions you could see at the definition 2 in that paper. Considering mu depends on x, split some x in a function u, strictly positive, and nu equals 0. Hence, they consider parabolic elliptic structure. The they consider in the first equation the term derivation of mu gradient of u plus f. In the second equation, he maintains that somehow the Darcy law, h of uv is equal minus gradient of p. Okay? In the other direction, Nikolai Shemitov and myself, in this paper of the generalized Book-Leverrier system, we were able to show the existence of X solutions, see definition 6.1 that paper, when mu equals f equals g equals 0, and nu is constant, just a constant, positive, that is considered a hyperbolic elliptic structure. So, Khrushchev has used a parabolic equation for the density u and elliptic equation for the equation of velocity. Yeah, in our case, we maintain the scalar conservation law for the density. It's very important, and we like to separate each specific density, but we plug a divergence in respect to the velocity. When you do this, we get more regularity with respect to velocity, and we could apply, for instance, the cinetic formulation for the scalar conservation law related for u. Okay? This is what you have already done in this paper, in 2013. Okay. So there are many difficulties, so we could not resolve the problem as from the beginning I show you, and then you start to think a little bit more when what to be done, and you have to think more about this problem many times. And then now I would like to tell you what are the new approach and the new strategy to try to resolve this problem. So we consider another approach to solve the Book-Leverrier system 1. So the original Leverrier system as I proposed to you, which is the stiff approximation or stiff limit solutions. Moreover, we are not going to apply the entropy formulation. I'd like to remember you that the entropy formulation is used to recover the uniqueness when you pass to show existence of a weak solution for scalar conservation law, for conservation laws, but the entropy formulation is not necessary to show existence of solution. Okay? So in fact, we are not going to apply this entropy formulation for the scalar conservation law. Our main motivation to use this approach comes from the paper. So this is the main paper you have used it in your case. So this is a paper from Benoit Pertin, Quiroz, and Vasquez, which is exactly the Harley-Shaw asymptotics for mechanical models of Turmo-Grove, which was published in 2014. So in fact, we take this idea from this paper, talking with Benoit, and then what this idea means, right? What is the main idea behind this? So in that paper from Benoit and Vasquez and Quiroz, they consider both the compressible and compressible mechanical models for Turmo-Grove. These two classes of models are related by using a stiff pressure law. See equation below. Just show you. So the equation 4, you could see that the pressure now is in fact given by some constitutive relation. So you are giving that the pressure depends now on u and a power law of u. So P gamma of u will be u a power gamma, for gamma bigger than 1. So these two classes of models, incompressible and compressible ones, are related by a stiff pressure law, as I said before, P gamma of u a gamma, and under some hypothesis of the initial data and so on, they consider the problem in the Cauchy problem in Rn. They succeed to pass to the limit as gamma goes to infinity, called the incompressibility limit or stiff limit in the compressible model. So they pass to the limit as gamma goes to infinity in the compressible model, and obtain a weak solution to the incompressible model, which is a free boundary problem of Harley-Shaw type. So this was done by Pertin, Quiroz, and Vasquez in this paper in 2014. Okay? So let us now present our strategy. So we consider a companion compressible model to 1. So like the incompressible one, we consider a closed system, which is a compressible model, due to a convenient pressure equation of state. Now P is given by a constitutive relation. More precisely, given gamma bigger than 1, let us consider the constitutive pressure having a power law in relation with the density U. That is, P gamma of U over power gamma, as I showed you before. So, under good assumptions on the initial data U0 of gamma and also F gamma, we expect that the family of solutions U gamma, P gamma of the companion compressible model will converge when gamma goes to infinity in some suitable sense, to be defined later, to an element infinity, P infinity, solve the Buckler resistance in the weak sense, which is, similarly to the per term et al. Cited paper, a free boundary problem of Hell-Short type, which I could say that is the geometric formulation of the multidimensional Muscat problem. I show you the weak formulation of the multidimensional Muscat problem, and this idea of the Hell-Short type solution somehow looks like the geometric formulation of the multidimensional Muscat problem, what is used to say the free boundary problem for the Buckler system. Okay, but one of you could ask us why I'm using a compressible model to resolve an incompressible model, since I used to hear for a long time that compressible models are much more complicated than the incompressible one, because using this exact type of pressure law, and send gamma to plus infinity, in fact, using this pressure law, you are gaining a system which is in fact a filtration equation. Looks like a generalized Ports-Meade equation. And we have a lot of machinery to resolve the generalized Ports-Meade equation. Somehow, we are using the compressible model to resolve the incompressible one, because you are taking for granted, for the beginning, the machinery already constructed for the filtration equation or for the generalized Ports-Meade equation. This is why the first answer, why we are using the compressible modes, is to be much more complicated than the incompressible ones to resolve a incompressible mode. I will show you what is the equation, in particular for the compressible mode, already written in this filtration equation idea. Okay, this is the main idea which is behind this compressible to incompressible case. Okay. So acquisition of weak solutions. Usually you are going to give the notation of Q, capital Q of T is 0T Cartesian omega. So the specific space-time cylinder, we are going to already denote the gamma of T is 0T times gamma. Frequently we are going to abbreviate, we are going to write just U for U of Tx and P for P of Tx. As usual, you are going to consider plus and minus function, the sign plus and minus. I'm not going to pass for this. I should pass quickly for that. Then we consider the main hypothesis. So we have two main hypotheses in this problem, in this contest. First one is the hypothesis A. So we are going to assume the following hypothesis on the nonlinear coefficients. So we have two nonlinear coefficients in this system. The first one is G of U, and H of U. So we are going to consider that these guys are Lipschitz locally linear. Could be more regular. I mean, it's not the main point here, the regularity of these coefficients. Okay, but we are consider, for instance, that they are Lipschitz, locally Lipschitz. So H should be bigger than some H naught, which is strictly positive because we are going to divide by H. G of Z should be used to be positive for Z positive, and G of 0 is 0. Okay, when Z is 0, G is 0. Moreover, we are going to assume that the capital theta of Z, which is already defined by G of Z of H of Z, is non-decreasing, and which is bounded and Lipschitz on compact subsets. So for compact subset Z, any compact subset, So this function theta of z is bounded and also Lipschitz. So this is an unusual assumption for the capital theta and also for G and H. And G8 could be a little bit more regular as you want. So this is hypothesis A. So the hypothesis B, and here, for instance, for the density, we follow this paper from Bertami et al. So we assume the following hypothesis on the data. First one, for some non-negative initial data U0 in L1, for some, I'm not saying that for any U0 in L1, for some non-negative initial condition U0 in L1, the initial data U0 gamma for the compressible model should be non-negative. The pressure P gamma at 0 should be, initial time should be equal to P gamma of U0 of gamma, which is less or equal to Pm is a pressure threshold. Yeah? We have in L1 convergence of U0 gamma to U0 as gamma goes to infinity, and further, you have a uniform limitation of the gradient of U0 of gamma in L1. So we have these 6 and 7 hypotheses with respect to the initial data, which is somehow given the exact way from the paper from Bertam, Vasquez, and Quiroz. Okay? Also, for the hypothesis B, you have this condition for some F, the normal flux, boundary data in gamma of T, there exists an F gamma defined in RD plus 1 plus, which is 0 infinite times RD, such that this looks like an extension. F gamma should converge to F in L1 of the boundary as gamma goes to infinity, and more than that, as before, to the initial data U0, for any compact set kappa, capital kappa, containing in RD plus 1 plus, RD plus 1 plus, you should have a uniform limitation with respect to the gradient of F gamma. See that F gamma is defined in our RD, okay? So this gradient with respect to X. So supremum of in gamma of the gradient norm, L1 norm, L1 log norm of gradient of gamma should be bounded. Moreover, we assume without logic and right that U0 gamma and F gamma are smooth functions, okay? To work with the compressible model in a more simple way. Okay, I should say the hypothesis A is quite general. In particular, the function capital T is non-decreasing, is assumed non-decreasing, is a usual assumption. Moreover, the hypothesis B satisfies a large set of functions. In particular, BV inter L infinity is contained in it. Okay, you could realize BV functions and you get the uniform estimate of the gradient of it. So now, in what follows, we define what is meant to be a weak solution of the Buck-Levy system. What do you mean by a weak solution? So definition of weak solution. So a pair of functions, E of tx and P of tx, such that with U in L infinity of Q of t, the gradient of P in L2 of Q of t, you'll be called a weak solution of the Buck-Levy system, one, when, so you integrate by parts the equations, so you have U times the text function phi of t, plus capital delta of U, gradient P dot gradient of phi, equal a boundary term, and this should be true for any text functions which does not see the initial data, but see the boundary. And also for almost all time t, in 0 capital T, the integral of you have the incompressibility condition in the weak form. I mean, divergence B integrated by parts, you're going to give you the gradient of B divided by H of U dot gradient of QC should be equal 0 for any text function QC in same infinity compact part of omega. Moreover, the initial data for the density U is attained in L1 strong sense, which means that the essential limit of time goes to 0. Here U is just an L-infinite function, so I'm going to take in an essential limit of it. As time goes to 0 of ut, the L1 norm of ut minus u0 is 0. Also, so if you have this, I'm going to tell you that this couple of function, the pair of functions u capital P, is a weak solution of the Buck-Leverage system. So our main theorem, under the above conditions, hypothesis A, B, the unique solution U gamma, P gamma of the compressible model converges strongly in L1 as gamma goes to infinity to some pair U infinity, P infinity, the limit functions, with U infinity, which is continuous in time in L1 of omega, inter BV of Q of T, and the pressure is BV on Q of T. So here should be continuous for 0 to T, capital T. The functions U infinity and P infinity assert that U0 is bounded from 0, from below from 0 and above from 1, and the P infinity from 0 in Pm, almost everywhere in Q of T. And also these functions P infinity to infinity satisfy a graph function P infinity times U infinity minus 1 should be 0. Which means that when P infinity is strictly positive, U infinity should be 1, and when U infinity is strictly less than 1, P infinity should be 0. Okay, so is the Hale-Saw meaning of this graphic relation. The gradient of P gamma weakly converges in L2 of Qt to gradient of P infinity as gamma goes to infinity. More than that, more interesting for us in particular, the gradient of P gamma in L2 is uniformly bounded. The pair U infinity P infinity solves 1 in the weak sense defined above definition, the above definition. And moreover, you have a regularity, the fourth regularity on the time derivative with respect to the derivative of U infinity in the sense of the finite measures on Q of T. And moreover, they have sign, so it means they not decrease. So this is our main theorem, and we try to show it. So we are going to give you, so I think I have more 12 or 10 minutes. So we're going to give you the main steps to show the existence of this problem, okay? So first of all, existence and uniqueness of solutions for the compressible model. So instead to work with the incompressible model, the original Buck-Leverage system, you are going to work with the compressible model. And I'm going to show you in the next slides. So what is our theorem? So let alpha bigger than 1. We are going to see what alpha is in a minute. Be a fixed parameter, arbitrarily, and let gamma bigger than 1. Under hypothesis A or B, there exists a unique pair U gamma P gamma solving the compressible Buck-Leverage system with initial condition 0 gamma and normal boundary flux F gamma. Moreover, for any gamma bigger than 1, we have this maximum principle for the solution of the compressible model U gamma and P gamma. Okay, so U gamma should be non-negative less than square gamma of Pm, and P of gamma should satisfy this condition. So let's just to give you a brief idea how it works. So instead to work with the incompressible model, we consider the compressible Buck-Leverage system written in the following form. So here you have the partial derivative with respect to U gamma is the Laplace of capital PC of capital PC is given by this function. So capital PC is a C2 almost everywhere function, so it's differentiated C2 almost everywhere. Okay, and it appears a term here which is a first term, scaled by this term of 1 of gamma at power alpha, and expect that this term will going to be 0 when gamma goes to infinity, to plus infinity. So the pressure relation to P gamma is equal U gamma at power gamma. This is exactly the boundary condition as before. It's just to differentiate the gradient of PC, you'll be PC prime, you'll be like here. So here is exactly you could see that to make the count is exactly you'll be gradient of theta of U gamma dot F equal F gamma, gradient P gamma dot N equal F gamma, and the initial condition U gamma 0 is 0 gamma. Okay? So we have plugged here an artificial bond, artificial first term, and as I said before, this looks exactly like a filtration equation or generalized Pauli middle equation. So with these in hands, you could apply the well-established theory from Benillan, Philippe Benillan, and then we are going to get an existence of to solution in L1, and since this species C2 almost everywhere, we get a strong solutions. We are able to work to multiply this equation for U gamma or U gamma power gamma and so on, because most of the times we are going to work with this. We are going to work with this function U gamma, or with the function, the equation for U gamma, or for the density, or the equation for P gamma, the density of the pressure. Sometimes it's interesting to work with the equation for the density. Sometimes it's interesting to work with the equation for the pressure. Okay. So this is the main idea behind, I tell you before, respect to the filtration question in the Benillan stuff. Okay? So first of all, you have L1 bonds for U gamma and P gamma. So let us assume that the hypothesis AB holds for fixed alpha positive, and for every gamma bigger than 1, U gamma be the unique solution of the compressible Bulk-Levy system. Then for any time t on 0t, you have a uniform bond in L1 of a gamma of your sequence U gamma, your family U gamma, given by this. Remember, this is the initial data. This is bounded uniform with respect to gamma. This is your boundary data is uniform with respect to gamma. And also, again, this uniform estimate of the pressure P gamma in L1 of gamma with this expression, which is also independent of gamma. Okay? So to get this estimate, you should work in particular with the density equation, and you multiply this density equation by the sign of U gamma, and you work with, and you obtain these two uniform estimates. This is not so different and should be easy to get. Then we pass to the Benillan-Aronson type estimates. Why we set type estimates? Because usually the Benillan-Aronson estimates, you have just the Laplace of P gamma. You could see this equation 17, and we do not have this capital theta of U gamma. It's a nonlinear term in front of the Laplace of P gamma, and this second term is a little bit more different too. So these Benillan-Aronson estimates or type estimates are very important to get estimates, in particular for the gradients in L2. Yeah, you are going to see this, and also to get estimates with respect to the second next uniform bonds for the time derivatives with respect to U gamma and P gamma. So this is one of the heart of the paper, one of the points which you have to work to get this equation, and we start this to get this estimate. In fact, you do not start with you start with the equation for the density, but we multiply by U gamma minus 1, and in fact you have to work with the equation for the pressure. Okay, after some many calculations, we end up with a Riccati equation, and then you could get these estimates from below. Okay. So this is one of the main points of our paper, to get this generalized Benillan-Aronson estimate with respect to the Bulk-Levy system, which is nonlinear system. Okay. Well, with this estimate from Benillan-Aronson, we could get this derivative in time with respect to infinity and P infinity. They are non-negative in the sense of distribution, just applying the Benillan-Aronson estimates. Then we pass so we get already uniform estimates in U gamma, P gamma. Then now we pass to uniform bonds with respect to time for your family of sequence. So under the assumption of main theorem, there exists a positive constant C depends on capital T, such that for each gamma bigger than 1, you have uniform estimates of derivative of U gamma and P gamma, you respect to in L1 And then to get these estimates is very important, since we are going to try to obtain uniform bonds in BV. So we are going to end up going to pass to the limit for sub6 in L1. First, you have to show these uniform bonds for derivative of your family gamma and P gamma. For that, we are going to use strongly the Benioff Rasson estimates too. Okay. Now it's also, as I said before, to get the BV estimates, uniform BV estimates, you have to show a priori estimates for the spatial gradients. Somehow, you have this proposition, the assumption of main theorem, there exists a constant C, a positive constant C that depends on capital T, such that for every gamma bigger than 1, you have this uniform estimate with respect to the gradient of the U gamma and the gradient of P gamma. So to get this estimate for the gradient, we are going to work with the dense equation, but in particular, you have to differentiate this equation with respect to x. And then you have to make some points when you differentiate this equation with respect to s. And I'd like to pick up one of these the estimates you have to use. So I pick up from this proof of this proposition, this point here. Which point is this? Since our boundary gamma is C2, you have assumed C2 regularity, the vector field n is a C1 vector field, Pauli function, and could be extended to a function capital N defined in whole RD, such that this capital N is a C1 vector field. You have this also the norm is less than 1. Then you could write the boundary term, the gradient of C of U gamma dot N. Now you could plug bigger N of gamma in on gamma T. Why are you going to do that? Because you have to have an estimate. We call that F gamma is also defined in our RD. Okay? So you have to have an estimate like this. The modulus of the gradient of the module of the gradient of PC dot N is less equal to the square of the dimension of your problem, d equal 3, 2, divided by this gradient of PC of U gamma dot N0. Remember that you have this uniform estimate of F gamma from below with this FB. This is used exactly here, so this is not good. The F gamma could not be zero in all of the boundary of your domain. So you are going to choose this estimate to get this estimate of the spatial gradients of U gamma and P gamma. This is also really technical to get these estimates, and I have to use this. Moreover, you see that this gradient of U gamma dot N minus F of gamma is 0 on gamma T. So it means that this constant on gamma T, and then the gradient of this function is parallel to the vector, to the normal vector field to your surface gamma T. But so these are stuff you have to use to show these estimates, the gradient estimates. So the compactness argument and property of the limits. So under the assumption of main theorems, it follows that your family of solution U gamma, P gamma of the compressible Volcker resistance converge strongly, passing to a subsequence in L1 as gamma goes to infinity to an element infinite by infinite. Moreover, this element infinite by infinite belongs to the BV. You already know that even if you have a W11 estimate, it does not converge in W1, does not converge even in BV, does converge strongly just in L1. So the following proposition tells us that in particular, U gamma infinite satisfies the Hellish-Shaw limits. So this proposition, when you have this convergence, L1 convergence, passing to also to a subsystem, we have a convergence almost everywhere. So under the assumption of main theorem, one has 12, which is the graph law, P infinite times U infinite minus 1 equals 0, and also these estimates, these uniform estimates for infinity and infinity, which passing to the limits as well. So, moreover, the function u infinity and p infinity satisfy the Hellisaw graph property, which is p infinity, infinity minus 1 equals 0. And I should say that Hellisaw graph property is very important to show the incompressibility condition. You have to use this because you are going to assume that, in fact, your p infinity is strictly positive, because if p infinity is 0 in an open set, you are done. So you are going to consider that p infinity is strictly positive, and then you have that u infinity equal 1, and for gamma sufficiently large, u infinity is extremely close to 1. So this Hellisaw property is very important, in particular, in this concept of the book-level system to show the incompressibility condition. So now there are two bounds for the gradient of p gamma and the weak convergence. So the theorem says that under the assumptions of the above theorem, compactness argument, the formula p gamma is uniformly bound in L2. Moreover, that p gamma converges to gradient of p infinity in L2. And here we use strong Debye-One Arasson type estimates. Just to recall you what are the Arasson. So in fact, we are going to multiply by p gamma and divide by theta of u gamma. You could do that. And then from 17, you are going to integrate by parts. So you have p gamma, Laplace of p gamma, integrate by parts. You are going to get minus modulus of gradient of p gamma square. And you could, using these Debye-One Arasson type estimates, we get a uniform limitation in L2 for the gradient of p gamma. It's very important. We are not going to show that p gamma converges strongly to gradient of p infinity, but it's enough to show that it is uniformly bound with respect to gamma. Okay? More than that, we could show a continuity in time and the initial strong trace. Under the assumption of the main theorem, then the weak limit to infinite given by the compactness theorem is such that, in fact, you have infinity continuous from 0 t with values in L1 of omega intersect with BV of TT, we already know. So it means that you have more regularity in your density. In more than that, since your solution u infinity is continuous in time, so there's no more necessary to be essential limit. You have the limit as t goes to 0 of the L1 norm of u infinity minus 0 is equal to 0, which means that your initial data is attained in L1 strong sense. Okay, this is already, it is very difficult from the paper from Benoit and Vasquez and Queiroz because of non-linear terms. And I should say that non-linear terms change everything. And then incompressibility condition. I'm almost there. I'm almost finished. So the incompressibility condition, we have to show that the U infinity P infinity given by the compactness theorem. So let U infinity P infinity be given by the compactness theorem. Then the pair U infinity P infinity satisfies the incompressibility condition, which is that the divergence of V integrated by part with the tax function equals 0. To show that, as I said before, we are going to use the graph relation P infinity times U infinity minus 1 equals 0. And then you have to use some two estimates, one from below and another one from above, because somehow we do not have strong convergence in L2. So we you could use just the uniform limitation of it, and also that the derivative of U gamma is bounded, also uniformly bounded. Okay, so we are able to show this incompressibility condition, in particular coming down the uniform limitation of the gradient of P gamma in L2, which, as I said before, comes from the Debye-One Arasson estimates. So finally, proof of main theorem. Finally, I think I have read past from the time. Finally, collects all the previous results. We can establish the proof of the main theorem. Oh, in fact, we have already done this. In particular, we perform a limit transition as gamma goes to infinity, called the stiff limit, and show existence of weak solution for the bulk leverage system. So we succeed to show the existence of solution to the bulk leverage system. And we do not going to tell you nothing in respect to regularity of the solution, regularity of the boundary, and even we are not going to tell nothing in respect to uniqueness of this problem, but we are under our radar and could be the next problems you could attack. And thank you very much for your attention. I hope you have enjoyed this presentation.
Thank you, Professor Vladimir,
Okay.
for the presentation. If anyone has any question, please raise your hand. No?
Could be.
I have a question.
Yeah.
There are some properties to the Buchler-Lever system between the scalar Buchler-Lever equation. I mean, for example, in the Buchler-Lever scalar, the fluxes is non-convex, and there are any type of the solutions, for example, rarefaction, shock waves, and other waves, singular waves.
You mean in
For
one
this
dimension,
system,
Richard? So, sorry, what do you mean? In one dimension?
Yeah,
Because
one
somehow
dimension.
your vector field is giving at least in two dimensions, yeah? Because somehow you expect that, well, what I could say with respect to the one dimension equation, it's not so makes sense because somehow you see that so V will be minus px h of u, v equal minus ph, v is just one. So divergence of v equals 0. E will be the gradient of v, vx equals 0, yeah? So v will be constant. You have this incompressibility condition, that the divergence of v equals 0. So if you have dimension 1, this should be vx equals 0. So v should be constant in x. So, I mean, somehow the problem become completely different. I mean, degenerates as well. Okay, there is not so much sense to yeah, because somehow your incompressibility condition, divergence of the velocity v equals 0, should be at least in n bigger than 1, 2, equal to 2 or 3, and so on. Okay.
Okay, thank you.
So somehow,
Duan,
okay. Yeah.
please.
Any question? There's no problem.
Okay, thank you. Thank you, Professor Never, for your very nice presentation.
Okay.
Thank you. I have a question. At some point, you mentioned that the regularity of the boundary, right?
Okay. C2.
At some point,
Yeah.
C2, right?
Yeah.
Then I just wonder if one can somehow make more weaker this condition. If one can go, let's say, if one can improve in terms of regularity.
Yeah, sure. You think that why you not consider rectangular? And yeah, it could be at least maybe there's no problem to pass for less regularity for by parts. I mean, locally, yeah. But since the problem, well, so it means that at least at the corners, the normal vector field will be not so well defined. But anyway, I think it could has less regularity for the normal vector for the boundary, but as well, I mean, I'd like to what another point which is very important, as you pick up a scalar conservation law and you regularize by the Laplacian, where you take the Venice viscosity idea, yeah. When you'd like to have the solution of the approximation equation of the Venice viscosity approximation, regular enough to multiply the equation by u, something eta prime of u, something like that. Somehow to get regularity, you have to have the regularity for the boundary. I mean, somehow I'm tell you, I'd like to avoid these technicalities to show more regularity for the approaching sequence, U gamma, P gamma, and so on, because of the low regularity at the boundary. Since the problem is already very difficult to show existence of solution, I'd like to if I need more regularity in G and H, it could be a C1 or C1 at least as well, because it's not the main point, the regularity of the data and also the regularity of the boundary of the domain. But okay, it's a good question. You could think that certainly, if you like to resolve real problems, or at least you could, if you have a rectangular, you could think that at least at the corner you could make a regularization of the corner, something like that. But it's a good question.
Very much.
I'd like to avoid these technicalities, and get the approximation sequence which are regular enough to for instance, if you go to the paper from Benoit, Bertrand, Vasquez, and Queiroz, you are going to say that they consider that you have enough circularity of the approach sequence, and they tell you nothing how you could get this. He assumed that there is a Cauchy problem. Does not have regularity of the boundary because it's not an initial boundary value problem. But as well, they did not tell you anything how could you get this approach sequence sense of this approach sequence. I see. Okay.
Thank you very much.
Thank you, Duvan, for your question. Okay. So I talk too much. People become.
I think no more questions.
Okay.
Thank you so much, Professor Vladimir, for accepting our invitation to the seminar. And we hope a new contribution in future.
Okay, thank you so much, Richard, and all of you, Duvan, Santiago, Tobias, and I'm sure that this will be a successful, meeting, and certainly you are going to have good or very well congresses in the next times. And I could help anyway if you need some help, and if I could help, could tell me anytime, and I will be here to try to help you. Okay, anytime as well. Thank you so much for the invitation.
Thank you very much, Professor Neves. Thank you so much.
Very much.
Okay.
Muchas gracias. Muchas gracias.
De nada.
Muchas gracias.
Duván, Cosier.
Okay. Muy bien. Bueno, luego de esta sesión tan maravillosa del profesor Neves, coincidimos con Richard, ¿verdad? Que podemos darle finalización a nuestro seminario, ¿cierto? Les estaremos enviando información del siguiente seminario por correo electrónico a los participantes que se inscribieron. Y bueno, estamos en contacto. Muchas gracias a todos los participantes que se unieron y que disfrutaron la charla del profesor Neves. Muchas gracias. Nos vemos pronto.
Muchas gracias. Hasta luego.
¿Quién levantó la mano por ahí?